to the lecture 18 in this course on noise control in mechanical systems, and in this lecture we will be starting a new module in this course, which would be a module on human response to noise. And to discuss about the human response to noise, we will study about various aspects such as what do you mean by human hearing, how do the humans hear and perceive the sounds, and what are some of the subjective metrics through which we can correlate how the human is perceiving the sound. We will also study how the sound affects the human. So, we will have both auditory effects of sound as well as non-auditory effects of sound, and a very common industrial hazard, which is noise induced hearing loss, will be introduced in this module. And then finally, we will see about, once we have understood and taken a grasp of how noise affects the human beings, then we come to know and understand that regulations are imperative in order to control the noise. So, the noise regulations already being enforced worldwide and in India will also be discussed. So, let us begin the very first lecture within this module, which is the lecture 18 overall. This is the lecture on Introduction to Human Hearing. Okay. So, here we will study, we will take an overview of what is the hearing mechanism, then we will see some of the perceived metrics such as loudness and the equal loudness contours, the A-weighted levels and the pitch. So, hearing is what? Sound is a physical phenomenon which relates to the pressure fluctuations travelling in the longitudinal wave fashion in the fluid medium. This then hits our ear then starts vibrating and transmits this information to finally the brain in the form of fluctuations in electric signals, and then our brain responds to this particular phenomenon. So, this response or overall this receiving of the sound by the human ear and the response to this sound becomes hearing, which is the subjective response to sound. So, over here you can see a brief overview of how a human ear looks like anatomically. You have an outer ear, then you have a middle ear, and then you have the inner ear. The purpose of the outer ear is to collect the noise. It is like an antenna trying to collect as much of sound waves hitting it as much as possible, and then whatever sound waves are hitting it, they are travelling through the outer ear canal and reaching the middle ear. So, if you see here, a length of this outer ear canal for a typical adult human ear is approximately 2 centimeters, and here it is acting like a rigid long tube which is closed at one end and open into an infinite baffle, which is the atmosphere. Okay. So, it is like a tube closed at one end and then opens up into an infinite baffle of the atmosphere, and this length is 2 centimeters. So, whenever we have got a closed boundary or in a tube the sound waves are flowing and suddenly a rigid wall is there, which means that the particles cannot flow through. So, in that case the velocity at this end would become 0, the particle velocity. So, which means that the pressure velocity, which is del p by, which is directly proportional to del p by del x, becomes 0. So, p is maximum, and here which finally it ends up meeting the atmosphere and diffusing, p becomes minimum or reaches the minimum value. So, which means that here the waveform can look like this. If p is a sinusoidal wave, this is a sinusoidal wave of pressure variation, then here we have the minima. So, it is the other way around, and here we reach the maxima. Now, if you think about it in the overall waveform, suppose this is your overall waveform like this, a complete sinusoidal wave. This part is a quarter of the wavelength, lambda by 4, and this lambda by 4 is 20 centimeter. If you solve it, lambda by 4 is equal to 20 centimeter, lambda being c by f, c by 4f is 20 centimeter, and taking c as 343 or 345 centimeters per second. Ultimately, when you solve it, what you will get. So, let me erase this bit over here. What you get ultimately is that the frequency maxima occurs, so the lambda corresponding to this, so the frequency corresponding to this lambda is approximately 4 kilohertz, and which is what is observed, that in the human ear, you know, they are most sensitive to the sound at 4 kilohertz. So, the sound wave has collected from the outer ear and reached into the through the ear canal into the middle ear. What is the middle ear doing now? Middle ear is sort of like a transition phase between outer and inner ear, and then it sort of tries to match the impedance. So, here we have air media, and here we have entirely brain fluid kind of a media and the nerve cells. So, from here to here there would be a lot of difference in the impedance of the two media, and this tries to match it. So, the impedance for continuity of flow, and this happens, this perfect impedance match happens at 1 kilohertz. So, once again the human ear is sensitive at 1 kilohertz. So, this is the range within which the ear is usually sensitive. Finally, whatever sound waves they are hitting, they are getting converted into the vibrations of the fluid surrounding this particular in the inner ear. These fluid vibrations, and then finally it goes through a very unique cell shaped structure called the cochlea. In cochlea what happens is that, depending on in cochlea what happens is that when the sound wave is hitting, depending on where it is hitting the cochlea, a different level of vibration is generated. So, in this membrane, if you sort of unstretch this particular cochlea into a long tube, so depending on which region of cochlea the vibrating waves are hitting, you are getting a different level of vibrations, and the distance at which they are hitting depends on what is the wavelength of the sound wave. So, which means that ultimately the vibrations in the cochlea are a function of the frequency of the incident wave. So, ultimately whatever sound which reaches our ear and the hearing mechanism, it acts like a frequency selective filter. So, we have a very complex frequency selective filter and we hear the sound. Okay. So, now we have, in order to quantify how a human ear is perceiving this so called objective sound pressure levels, we have some measures that have been devised. So, some of these measures which closely relate to how a human ear is perceiving are loudness, A-weighted levels, pitch, and then the quality or the sound quality. So, loudness and the A-weighted levels, they typically correlate, or they are sort of like the subjective version of what is the amplitude or the pressure or the intensity of the sound, and then pitch closely relates to what is the frequency of the sound or the frequency content, and sound quality, well, it is both time and frequency distribution. So, it is the overall spectral distribution of the sound. So, let us start with the very first matrix, which is the sound loudness. So, what happens? How do you define the loudness? So, think about it. Suppose you have some speaker is playing, and as a listener you say that, oh, please turn that off, it is too loud. And then suddenly some good music is coming up and you say, okay, it is very quiet, turn the volume up, let the sound become slightly more louder. Or you say that, okay, that person is talking loudly, or that machinery is too loud. So, this is a very common terminology we usually use for noise or sound, that something is loud or quiet. So, what does this loudness mean? It is the human's subjective response to the sound pressure or the intensity that is hitting them. And if it was some objective measure like the SPL or the decibels, okay, so then you will directly say that, okay, so that means that loudness should be directly proportional to the the acoustic pressure or the intensity, but that is not the case. Loudness is not always directly proportional to the acoustic pressure or the intensity. It depends on the pressure or the intensity, but there is more complexity to it. Because why? Because of this fact that we are hearing it through this entire mechanism, and in this hearing the vibrations generated with, or the sound the brain signals generated by the different sound waves. They also depend, that they don't just depend on the acoustic pressure of the sound, they also depend on the frequency. Okay. So, hence maybe there are two sounds of the same decibel levels which are hitting us. In one sound the frequency content is something different. Let us say one sound is somewhere around 4 kilohertz, and then there is another sound of the same decibel, but the frequency is at let us 20 hertz or 50 hertz. Then to our ear the 4 kilohertz sound will actually sound much louder than the sound at 50 hertz and so on, although they both may be having the same SPL, because our hearing is also dependent on the frequency. So, in the same way, the loudness is a function of both the sound pressure of the wave as well as the frequency of the wave. Okay, based on a lot of cumulated research on human hearing, and listening tests where people were given stimuli with different levels and the sound stimuli at different frequencies, and numerous such studies were conducted, and people were asked to judge the loudness of the sound, whether this is louder than this or that. And based on that, finally over years and years of research, this equal loudness contours were made. What do they show is that these are the lines of equal loudness which is felt by a human being. So, if you look here at one particular level, let us say at 60 dB. So, let us say we are giving the human ear a sound of 60 decibels. If that sound is close to somewhere around 4 kilohertz, which is this line here at 4 kilohertz, so it sounds that 60 decibel sounds at 4 kilohertz, it sounds greater than 60. And similarly, in some of the in this entire region, if you see that same 60 level sound will sound like 60 decibels or greater. But if you shift towards the lower frequency, then what happens? That same 60 dB sound will actually sound lower. So, this is a 60 decibel sound. Here this means it is just barely audible at this frequency, and the same 60 dB sound as you go higher, so suppose say at 100 hertz, it corresponds to a loudness of 40. The same 60 dB hertz at this here is barely visible, which is at 40 hertz, is barely audible here, but over 100 hertz it is almost close to 40 dB or sorry 40 loudness, and then as you go up towards this more frequency sensitive zone, it becomes louder, and then again as you come towards the high frequency zone, again that same sound would be of less loudness. So, basically if you see or observe the pattern of this curve, here the dip indicates that the human ear is more sensitive to that particular frequency zone, and that is why it is more sensitive. So, this is the equal loudness contour. So, even at lower frequencies you get higher loudness in this level, and here even at higher SPL you get the same loudness. In fact, most of the human hearing is based on this equal loudness contour. This shows a graph. So, this is like a typical threshold of hearing, below which human ear is roughly insensitive and they are not able to hear the sound. So, this becomes a threshold of hearing, which is also called as the threshold of quiet, and this upper one is the threshold of pain, and in between there are sounds at different ranges like the speech, the music, and this is the limit where the damage happens. So, that is what you mean by loudness, that is how loud the human is judging the sound to be, and it is a function of both the SPL as you saw here, it is a function of the SPL and the frequency, this loudness. Okay. So, how do you, in order to quantify this loudness, zones were proposed. These are a certain units to quantify the loudness, and how do you do that? For that you use a different frequency scale which is called as the critical frequency band. This shows the critical frequency band or the Bach scale. This is a scale which corresponds very much to the human cochlea, where the different frequency bands are there and equal distances within these frequency band. They correspond to the human ear's equal loudness difference. So, as you jump from one band to another band in this bark scale, you get, it's like jumping from one loudness to the another loudness value. So, it is like showing a scale where loudness is increasing linearly. This is like a scale. So, what happens in this critical scale? You simply integrate. So, first of all, you represent the sound signal in the 1/3 octave spectrum, and then this is the 1/3 octave spectrum, and then you combine them into critical bands. So, you obtain a new bark scale, and then in the bark scale some special kind of spectral weighting is applied. It is a complex algorithm, and these algorithms are available online as well, which you can go and search. So, the spectral weightings are applied, and all of that has been determined based on the hearing research, and after that you get, after applying the spectral weighting on that sound spectrum represented in the bark scale, you get a graph of specific loudness, which is like loudness per critical band, or the loudness increase with increase in the critical band. So, you get the specific loudness, and when you integrate it over the entire bark scale, you get the total loudness N. So, this formula gives you the loudness in sones, which is the SI unit of loudness, but the more typical or commonly used unit is also called as phones. As you see here, the equal loudness contours were first devised with phones in mind. Okay, so, this was the phones, which was an older unit of loudness. And how are sones and phones related? Using this formulation here. So, this is the loudness in phones, which is 40 times 10 log 2 of 10 n, where here this is the loudness in sones. So, let us say this is one graph that I had made in Excel, where I had a sound signal. So, basically I had, some pressures points at different frequencies, all having the same intensity, which is 60 decibels. Okay. And then when I applied the loudness algorithm to it, which is available online as well, it is too complicated to show in this introductory lecture, and hence I have kept it out of scope of this course. But when you apply that particular spectral masking and the various algorithms, what you get is, you get this as the specific loudness in phones. So, if you see here this curve, it soon looks a bit familiar. What is this? If you come here, this curve is the inverse of the equal loudness contour. Okay. So, that simply means that a 60 dB sound when passed, it will be barely audible at 10. That same so it might be having same 60 dB at 10 frequency, but it would be barely audible. It will feel like it is just 0 loudness in phones. And then as you increase or go up in the frequency, it will, the perceived loudness of this noise will start to rise, and then within this sensitive zone, it will sound same as a 60 decibel sound. It will be of 60 phones loudness, and then once again, once the frequency goes beyond this value, the perceived loudness decreases. So, this shows how sensor, even though I am passing a signal of 60 dB throughout all the frequencies, our ear hears it like this. It hears it as a sound similar to 60 dB only within this sensitive zone, which is this frequency here between 1000 hertz to 4 kilohertz, and below that the same thing, the loudness decreases so that it is barely audible below 10 or 50 hertz, and then suddenly the loudness also drops at some higher frequencies. Okay. And now that you have this graph in phones, if you apply this formulation here and you have this in phones, if you convert it back to sones, you get this specific loudness in sones, and so this is what? This is your N dash in sones that you are getting, and if you integrate it to get the total loudness. So, once you integrate it, the area under this curve becomes your total loudness, which is 19.5 sones. So, you see that although I passed a 60 dB noise at all the frequencies, ultimately it boiled down to being 19.5 zones overall. So another matrix that we use, same as loudness, is the A weighted levels. In fact, this is a more common choice by the noise control engineers and researchers. So just like the equivalent sound pressures are represented by L equivalent or LEQ, the A weighted sound pressure level is given by LAEQ. Okay? And how it is obtained? You have, let us say you have the sound spectrum in 1/3 octave. You apply some spectral masking, or that is means you apply a spectral weighting to this sound and convert it into A levels and then combine them together. So, what do? You represent the sound in the 1/3 octave and then you apply a frequency selective filter to it. So, how should this filter look like? It is like you are applying some weight to every level at every frequency band. So, if this is your original waveform, let us say, okay, in the 1/3 band, now you add some factors to each level, these WIs to each frequency band, so that it should mimic the human hearing, and this is what the human hearing is like. It is more sensitive towards this 1 to 4 kilohertz frequencies, drop sharply at the low frequencies and again has a small drop at the higher frequencies. So, this is how the human ear hears the sound. So, that is the same type of frequency weighting you have to apply. So, what it means is that at the lower frequencies you need to have this WI should be a high negative term. You are sort of subtracting the levels, because the human ear, to a human ear at these low frequencies they will sound very low, but they will sound the same level at these middle frequencies, and again their perceived levels will decrease at higher frequencies. So, you have to apply these weights. This is the generic function to get the weight at every 1/3 octave band level. Then you use the formula of combining all these levels to get your final LA equivalent. So, this shows us the weight. So, as you see here and as already anticipated, at lower frequencies we are reducing the actual levels to get how the human ear perceives it, because it is not very sensitive at these frequency ranges. So, we are adding these high negative terms, the highest at the lowest frequency and then slightly decreasing as we go ahead, and it keeps decreasing, and then from here onwards we have the sensitive zones. So, our the decrease in the level, the factor by which we are decreasing the actual level keeps reducing, and at 1000 hertz it is 0, no decrease, and then it is more sensitive at this range. So, instead of decreasing we are now increasing the levels. So, from here onwards whatever was the actual levels we add a positive weight to actually increase it, because our ear is in the sensitive zone, where this zone over here, these sensitive zones where the sounds are perceived much louder. So, again we reach the sensitive zone. So, we add small values to it, we keep doing that for these sensitive zones, and then slowly as we move away into higher frequencies again we start reducing the amplitude, because then again the sensitivity reduces. If you can see it in this graph, again once we reach a certain level this perceived loudness slowly drops. So, we will reduce the actual levels like this. So, suppose I have the same signal 60 decibel in all the frequencies, and now I already obtained the graph of the specific loudness in phones. Now, let us also obtain the graph of this in dBA. So, what I did was, to these levels in the various bands I have added these factors. So, this is how I have added these factors to 60 dB. So, in the 20 hertz it would be 60 minus 50.5, in 25 hertz the level would become 60 minus 44.7, in 31.5 this level would be 60 minus 39.4 and so on. So, this modified level will give you a graph like this. So, you see that this A weighted graph is very close to the human's loudness perception. So, this is a very close indicator of how the human ear is actually perceiving the loudness. Okay. Now, the last for this lecture, the last measure is the pitch, which corresponds very much to the frequency of the sound. So, this is what? This is the subjective perception or the subjective response to the frequency. So, low frequency sound means for a human it is like low pitch, and a high frequency for the human it seems like it is the high pitch sound. Some examples I can give you, like the pitch of a female voice is usually perceived as higher than males. When the female is talking, we say that, oh, that's a high pitch noise, and when a male is talking, in most of the cases you say that it's a low pitch noise. In the same way, in a machinery or in a mechanical system, the mechanical machineries, they usually have more of the low frequency content compared to a high frequency content. So, to us the pitch sound, it sounds like the mechanical machinery are low pitch, whereas the electronic machinery, they have a higher pitch or more kind of high frequency tone. Okay. This is the typical range of frequencies and some of the typical sounds. Okay. So, like the rotating machinery, the table radio, the speeches, male and female voice, where female voice is almost double the frequency, so sounds like double the pitch and so on. Okay. So, I think with this I would like to close this lecture. So, thank you for listening.